So it's not super critical that you nail it this instant, but the sooner or the more familiar you are with those functional groups, the better off you'll be in the long run. Okay? And that's where we ended last week, which is where we're supposed to start here. Looking at some interactions. We're a little behind, so I'm not going to address those top two interactions because those top two were in the play posit. Okay? The bottom left one was in the play posit, okay, which caused a lot of people freaking out. Okay? So we're going to skip that one for the moment too. And we'll go ahead and look at the lower right corner. If we were to look at these two interactions, which interaction would be preferential? Would I expect that black bond to interact with the red bond in that way, carbon to carbon, or would I expect carbon to oxygen, purple bond? So we got red or blue? Okay, we got a little bit of a mix there. It should be going towards the blue. Okay? Why? If we evaluate differences in electronegativity within each of those bonds, we should note that the oxygen is much more electronegative than the carbon, which means our carbon builds a large partial positive, the oxygen builds a large partial negative. That same interaction is being generated on our sister molecules. Why is that relevant? Well, what happens is I'm going to align a positive to a negative, or I'm going to align a positive to a positive. Okay? For those of you that have gone through and done the hybridization reading, that could be confusing because the positives and negatives mean something else in hybridization theory. Okay? But what we're looking at here are partial charges. Opposite charges attract. Okay? Why would they attract? What happens if I put a positive next to a negative? They become neutral. Nearly all things in chemistry are trying to become neutral. That's how and why they react. Okay? So us as humans, what do we try to do? We try to separate the positive from the negative as much as humanly possible. Why? What's going to happen? Those things are going to naturally come back to each other. As they come back to each other, what can we do? We can harness that motion, like we've done with water. Okay? We naturally build dams and power plants on rivers. Why? What's the water going to do? You've seen rivers, right? I know we're in Arizona. They flow from the mountains down to the larger bodies of water. That's a natural tendency. And we put facilities in between to take that natural motion and turn it into electrical energy that we can now manipulate. We do the same thing with charges. That's what a battery is. Okay? We've separated that positive from negative, and we temporarily held it there such that we can then put it into our devices and power our devices. Okay? Same thing's happening kind of at a chemical level. Those things are going to try to interact with each other. Okay? We get a vast variety of different positive negatives naturally because there's lots of different things happening. Okay? And different concentrations in different locations are going to allow things to balance out. Okay? So if we look at these, the two interactions that are most favorable is positive to negative. The blue one is the more favorable interaction because it's canceling that charge. The red one doesn't cancel the charge, it only makes it more positive. So that's a less favorable interaction. Kind of, sort of? Okay. If we compare that out to the other example, like I said, everybody's favorite, and we look at our carbon to hydrogen, I'm going to undo that I did that. We could do the same kind of situation. Does our hydrogen prefer to interact with more hydrogen, or does it prefer to interact with carbon? Which of those interactions is favored, top or bottom? Right? Directly from the play posit video, and if you selected bottom, you were wrong. So bottom is not the correct answer. So which one must it be? Okay, it's neither. Okay, not really neither. It's not top or bottom in preference. Both. There's zero preference for one or the other. There's no charge being generated. Okay? In that carbon-hydrogen bond, we don't get a difference in charge. No charge means there's very little need to interact with anything else. Okay? So neither of those is really preferential. They're both equally available and equally preferred. Okay? What would we describe that interaction as? Strong or weak? It should be relatively weak because there's no reason to interact. Right? And if you listened carefully, we heard someone suggest it doesn't want to bond. I want you to be a little bit careful with the use of bond. Right? We're not talking about a bond here. We're talking about an attractive force. These things don't want to interact with each other or don't have a driving need to interact. If we go to the other example with our OC, that interaction is now strong or stronger. Okay? This is one of the things that's difficult, is that we're using relative terms. This is a stronger interaction than this one. Why is it a stronger interaction? Okay. There's partial charges to cancel out, right? I don't know if it's bothering you, but it's bothering me. Let's get rid of that one. Yeah? So that makes it a stronger interaction. Okay. Does that make it a strong interaction? Not necessarily. We'd have to look at a more quantitative scale to establish that. Okay, what are all the possible interactions? Kind of make sense? Okay, so what are all the possible interactions? List any one you know. Van der Waals. Okay. We'll step through all that. Heard reference to Van der Waals, also known as London dispersion. Also known as induced dipole. Why are there so many names for this one? Any ideas? It's one of the weakest interactions. It was so weak that what did we do? Was that it didn't exist, and we ignored it until Van der Waals came in and was like, oh, this is actually kind of important. You need to evaluate this. Okay? So it then starts to pick up some of his name. And we're like, it's dumb to name things after people. Okay? I kind of agree with that logic. We need a different name. That's where we're getting maybe London dispersion forces. I honestly have no idea where London's come from. It's like, well, why the hell are we mentioning London? And we get induced dipole, which makes a lot of sense, except it's way too long. So we end up with just a mess of different terms for those. I personally go with LDF. Okay, London dispersion force. Okay, what other forces or attractions do we have? Okay, we've got dipole. We've got hydrogen bonding. Noticing a pattern here. You could have said yes, or you could have said electrostatic, ionic, polar covalent. Everything on this slide is an attraction. Okay, it is an interaction. They all varying with different strengths. Some of them are very strong attractions. Some of them are very weak. Where's the weakest? Okay, our London dispersion was our weakest attraction. Where's our strongest? Our strongest is our covalent, sometimes also known as non-polar covalent. That seems kind of weird. We put the strongest right next to the weak. Why? Is there a difference between the covalent attraction and the London dispersion attraction? Yes. What's that difference? Force versus bond. Okay, that's cool. So you're using new words that don't have any meaning. Or we could try intra versus inter, which theoretically have more meaning than bonds and forces. Intra is within a molecule. What attractions are we going to get within a molecule? Those are bonds. Between different molecules, what are we going to get? That's our forces. Right? So we have two major category differences between these. We get our bonds, and we get our forces. And what's happening is we're moving from our weakest attraction all the way around to our strongest. Okay? Why not show them as a straight line then? Why show this pattern side by side? Show a comparison. What do you mean? What did we show that had that weak attraction? That attraction was the weakest attraction. That's our London dispersion. What kind of bonds do we have in that compound? Okay, here reference to a hydrogen. Yes, there's a hydrogen. Hydrogen does not count as a bond because we have ionic, polar covalent, and non-polar covalent. Hydrogen would be, at best, a force. Like, but it says bonding. I don't care. It's a bad name. It's not a bond. It's a force. Okay? I don't care what your biology teacher tells you. They're wrong. Okay? It's a force. That bond is a non-polar covalent bond. What if I have a dipole-dipole force that is slightly stronger? Good example for that. That attraction counts as a dipole-dipole force. What kind of bond do I have between the O and the C? That was a polar covalent bond. Each of those forces are direct results of the bonds that made up the characters. That was said horribly. Did you get the idea? Okay. So if we can look at a formula, or better yet, a Lewis structure, and we can predict what bonds are present, we can now predict something about their forces because there's a direct correlation across. Yeah? Okay. Define each of those terms as best you can. Okay, what do we got? Anybody got a definition that you want to share? So we've got a dipole-dipole attraction between a hydrogen and an oxygen. I'm going to have a couple problems with that definition. Okay. The first is that it is very specific. Okay. Being so specific, you're now not going to be able to apply that to something else. So the definitions that you should be trying to define and nuance would be ones that are applicable to lots of different structures. Okay. So the next thing that I might complain about is if we had that interaction, it's actually better labeled hydrogen bonding. Okay? So I would argue that definition isn't going to hold too much water. How can we make dipole-dipole better?
So it's between one not electronegative atom and then one very electronegative atom. It's like differences in electronegativity.
We do need differences in electronegativity.
But big differences, isn't it?
Is there a big difference there between the oxygen and the carbon? Yes. Is this a dipole-dipole in purple?
I don't think so.
You don't think so, right? Why not?
Because the hydrogen isn't, like, how do I describe this?
I can help. Let's see if this helps. Let's do the red one. The red one is often known as a dipole. The OC is referenced as a dipole because there's a large difference in electronegativity. I get a partial negative, partial positive. So that establishes a dipole.
It's a non-polar covalent.
This bond is a non-polar covalent, which means we do not get a dipole. So I have not dipole-dipole. Is that a dipole-dipole force? No. So we have to be careful with the terms that we're using when we go through and make these definitions. The best way to go through and reference this, okay, it's a polar covalent bond interacting with another polar covalent bond. Okay? This is why they're next to each other. Problem with that definition. What is a polar covalent bond?
Electronegativity between 1.7 and 0.5.
Awesome definition. Textbook definitions. Difference in electronegativity for a polar covalent bond between 1.7 and 0.5. What is the electronegativity of phosphorus? Definition doesn't hold water. Okay? It's everything else. So this is why you can watch the videos and you get this great definition. Polar covalent is everything else. That becomes a problem because what the hell was everything else? Okay? So we have to have some way to go through and qualify these. You can use electronegativities, and in the strictest sense, it is absolutely valid. But it is too difficult to memorize all those electronegativities. You only have so much brain space. Best definitions that I would recommend: ionic, metal, and a non-metal. Okay? It's not perfect. Look for charges. Typically, the metal is a way to hide the charge. That's why metal and a non-metal works. Okay? Covalent, better classified as non-polar covalent. Okay? Difference in electronegativity, less than 0.5. Probably the most important one is carbon to hydrogen, is classified as non-polar covalent. Okay? And same to same. Same to same is important. You just don't see it as much. Carbon to hydrogen you'll see everywhere. Right? How do you know you have an electrostatic force? You had an ionic bond. Directly correlates. How do you know you had a dipole-dipole force? Because you had polar covalent bonds. How do you know you have London dispersion force? Because you have non-polar covalent bonds. Okay? Or carbon to hydrogen. So we've got 6 things up here, and you really only need to know 2 definitions. Okay? You don't have to know exact pieces, but you do have to know those relationships. Kind of make sense? Okay. To be London dispersion, okay, we'll typically reference that as non-polar covalent. Ultimately, the action of what's happening within these is a little bit more complex than just saying it's coming from that. Okay? London dispersion, or induced dipole, is talking about how the electron clouds move. How many molecules have electron clouds? Every single one, which means they all have London dispersion forces. Okay? That's not a false statement. But if I have a polar covalent bond, do I care about the London dispersion forces? Probably not, because the dipole-dipole force is more prevalent. Right? So all molecules will have London dispersion because they have electrons. If you have an electrostatic force, is it possible to get dipole-dipole and London dispersion? Yeah. Do I care? Okay? And so a lot of it comes down to the nuances of what's relevant or not. We're typically concerned about the strongest force. We'll then downplay as needed. If the question is, what are all the possible forces that this thing can have? Now you really got to narrow down into each of those definitions and zero them all in. The utility of that question, very small. Does that make sense? Okay. Make sense? We good-ish? Cool. Which gets us to what I think is my master stroke. Cool slide picture. Not everybody likes it. You don't have to like it. But what we're trying to show is the relationship of going from London dispersion forces all the way around to our nonpolar covalent bonds. It's also color-coding the interaction across bonds and forces. Okay? This is a better way to represent it because we tend to get locked in, oh, that's only London dispersion. Oh, that's only dipole-dipole. Okay? We're looking at the sum total of all possible interactions. This is really just one perfect continuum, straight line. And scientists have now dropped in artificial boundaries. Right? Those artificial boundaries work because when we predict things based off of that boundary and we're right, that's a good boundary. What happens when we predict things and we're wrong? Not a good boundary. Move it. Okay? So over time, those are the boundaries and categories that we've come up with. Why is it important to have an understanding of these? Well, our first unit was talking about what? Lewis structures. And what do we see in structures? Bonds. Virtually the rest of the semester, we're concerned about how that molecule interacts with the rest of the world. Okay? Melting points, boiling points, solubility, pressure, reactivity. Super important one for us. That's how that molecule talks to another molecule. That's not about bonds anymore. That needs to be about forces. So if I understand what bonds are there, I can predict forces, and I can thereby predict all sorts of other cool things. Right? So melting points and boiling points. What's resisting a phase change? Here's a solid. One molecule of solid. Where do I draw the next solid molecule? And the next one? When I turn this into a liquid, what has to happen? They have to spread out a little bit. Not a lot, but they're spreading out, right? Sometimes they're stuck, sometimes they aren't. I'm not going to keep drawing them. What's causing that? So what broke? We get a lot of people saying it's bonds that broke, which is complete crap. If a bond broke, what would my picture at the bottom look like? Half circles, pie shapes. That's breaking a bond. When you're melting, you are not breaking bonds. Phase transitions don't destroy the molecule. What are they breaking? The connective places in between, which is your intermolecular forces. So if I know what those forces are, I can predict something about the phase transition. Right? So let's say I look at that red circle, and that red circle is made up of sodium and chlorine. What is my connective tissue going to be? What are those blue lines going to be? Electrostatic, okay, or ionic. Doesn't really matter for our forces. Okay? Is that a strong force or a weak force? Strong force, which means how much energy do I have to put in to cause that molecule to rip away from the other? A lot, which means the melting point goes really high. Right? What if instead of it being sodium chloride, it's now methane? When we look at the bonds within methane, they are nonpolar covalent, which means when it interacts with another methane molecule, we are looking at a London dispersion force, which is incredibly weak, which means very small amount of energy to put into that, which means our boiling point is very low, or our melting point very low. Okay? Are there exceptions? Yes. Okay, there's other things that resist phase change. Right? Let's upset the tube in the center. Why not, right? You're welcome. Feel free to report me. Here's our substance, two substances. We're going to have them interact with each other, right? Where are they interacting? Okay. Where are they interacting? We could put that up to the microphone because it sounds really scratchy and annoying, and that would really irritate people at home, right? Where are they interacting? Where are the two pieces of paper interacting with each other? Are they interacting out here? No, why not? There's no paper there, okay. Are they interacting right here? This top paper is interacting with the bottom paper up here. No. Where are they interacting? In between, where they are touching. That would be the surface area, right? How much surface area do we have between these two pieces of paper? Good amount. There we go. I like it. Way to be generic. Do we have a different type of force here? No. Why no? I like that. Our paper or our forces and our bonds have to do with what made the substance. What makes these balls? Paper. What made these paper? Is the force different? No. Are they going to have a different interaction? Yes. Why? What is that shape changing? The surface area contact between those now changes. Because that contact changes, does that change the amount of energy it takes to separate them away from each other? Yes. So it's not just the strength of the force, it's the amount of times that force can have an effect on our overall structure. Okay? That's nuts. So Lewis structure becomes really important because I can take the same 5 carbons and I can change their boiling points and melting points just by changing the locations of those carbons. That's a really big deal. Okay? So when we're looking at our forces, it's never just as simple as, it's just strongest or weakest. It's also factoring in things like shape. That's why we talked about Lewis structure, because we have to understand that shape. Okay? We can also see it with solubility. I want 2 things to mix with each other. Okay? If I take my solid, bear with me, and my liquid, and I want them to mix, what would it look like? I want them to mix. What would it look like if I mixed those? They interact with each other. So you mean like this? And now they are mixed. Okay. That doesn't really look homogeneous, right? That looks pretty heterogeneous. They're very clearly separated away from each other. How can we change it? Artistic rendering. Okay. What's changing as we move from them separated to mixed?
The liquids in between.
Okay, what changed to cause the liquid to get in between? The forces, okay, had to change. I have to break the connective force between each of those and each of these so that I can make a new force. Yeah? Okay. For me to make that new force, it must be more stable than the original. Okay? Which means for them to mix, we must be canceling out those charges. Okay? Or not having charges be there at all. So this is why when we mix water with, say, ethanol, what happens? Water with ethanol. Some people should know this answer already. If you're under 21, wait a couple years. Thank you for keeping that quiet. Enough. Those 2 substances mix. Why do they mix? They both have what?
Hydrogen and oxygen, so like.
I kind of accept that they both have hydrogen and oxygen. I'd like you to go a little bit better than that. They both have hydrogen bonding. They both have similar forces. So when you've heard that like dissolves like, it's like forces dissolve like forces. So you have to be able to identify the forces in each compound. How do we identify the forces? We had to identify the bonds first. Okay? So we have to dig 2 or 3 sections back to get those relationships. Okay? So they both have hydrogen bonding, right? So they mix, right? So they still both have hydrogen bonding. Yeah. How about now? Do they still mix? Some people are laughing. You're only laughing because you aren't drawing it. Do I still expect them to mix? Do I still expect them to mix? What is that? It's a bunch of freaking carbons with hydrogens on it. Do I still expect them to mix?
More unlikely.
It's more unlikely. Why is it more unlikely?
There's more stuff in the way.
There's more stuff in the way. What is that stuff in the way doing?
Blocking the force.
It is blocking the attraction between that one OH and that OH. We're minimizing the ability for the hydrogen bonding to interact. So if you want to say it still mixes, that's okay. Does it mix as well? No. Good. Good first step. Now what you got to do is go to lab and you got to test it. You guys are horribly wrong. Those don't mix. Not at all. Okay? So at some point, they switch from mixing and not mixing. Where's that some point? Hearing a 4 to 1. What's 4 to 1? Odds in Vegas. Okay, 4 to 1. Number of carbons to hydrogen bonding. Why do I care about the number of carbons? What are the carbons contributing? Are the carbons contributing charge? No, why not? I don't know. Come on, you can do better than that. Why would the carbons not contribute charge? What can you tell me about the carbon-carbon bond and the carbon-hydrogen bond? They are nonpolar covalent, which means the difference in electronegativity is next to nothing, which means there's zero interaction. Doesn't want to interact with anything. Doesn't want to interact with anything. If there's enough of them, what does it prevent? Anything to interact. And it shuts down the solubility. Okay? Someone went into the lab and tested this enough and noticed that there's an approximate pattern. Roughly 4 carbons outweigh 1 hydrogen bonding interaction. Okay? With people getting too specific. Roughly, in big words, roughly. Okay? Very ballpark. But it gives us a decent estimate that we can then see how our solubility is going to change. So that when I get up to a crazy compound like that, that doesn't mix well. But if I start to clean up and remove some of those hydrogens, it increases in solubility. Okay? It may not be perfectly soluble yet, but it increases. Okay? Until eventually, hey, now it dissolves because there's only 3 carbons, 1 hydrogen bonding. Yeah? Okay. So, again, is the force the be-all, end-all? No, other things can contribute. We're looking at the overall picture. Water just has hydrogen bonding. Propanol, as I've sort of got drawn here, has hydrogen bonding and nonpolar covalent bonds, which lead to London dispersion forces. If I get enough London dispersion forces, they will outweigh the significance of the hydrogen bonding. Okay? So, like dissolves like. So, solvent terminology. A lot of what we do in OChem is labeling solvents so that we can run reactions. Most of the time, we don't run in water. Why not? Water's polar. Water is also, what was this class? Organic chemistry. Water is not organic. Right? So we tend to use organic solvents. There's other reasons behind it. So, solvent terminology. You've probably heard reference to polar and nonpolar. They are awful terms. Okay? Get that out of the way right out of the gate. Okay? You should rarely be referencing anything as this is a polar molecule and a nonpolar molecule, because that makes it sound like it's black and white. It's not. It's this massive gray area in between. Right? It is more polar, it is more nonpolar. Right? What are we referencing when we say it is polar? Sort of charges, slight charges, partial charges. Where do we get partial charges? That's a B, not a P. Polar covalent bonds. When you look at the molecule, does it have polar covalent bonds? Yes, it is probably a polar solvent. Right? Are there things that prevent that? Is that a polar covalent bond? Is that compound a polar compound? No. Why? The dipoles cancel each other. So we have to consider molecular shape when we go through and look at these things too. Okay? You mean chapter 1? Yep, chapter 1. Okay? What is a nonpolar solvent? Carbon to hydrogen is an example of, yes. CH4 is now a molecule. Still going the example route. What is a nonpolar solvent? Nonpolar covalent bonds. So carbon to hydrogen was great because those are nonpolar covalent bonds. Okay? So what we're trying to do is look at a formula to come up with a bulk classification that can help us approximate this. Okay? Did we have nuances within the nonpolar covalent category? What types of forces were available to a nonpolar covalent bond? London dispersion. So is there a difference for nonpolar? Rhymes with snow. No, there isn't. Okay. How about the polar covalent bond? Was there a difference in forces possible for a polar covalent bond? Yes, it could be dipole-dipole or hydrogen bonding, which means polar as a solvent class could be refined to look at a solvent that is so polar that it has hydrogen bonding, or not quite as polar because it has just dipole-dipole. So it might be useful to add another name to clarify that polar solvent. That polar solvent name comes directly from that extra solvent, hydrogen bonding. What are we going to call it? Hydrogen bonding, meaning it has what? Hydrogen bonded to oxygen, nitrogen, or fluorine, right? Let's flip that up just because it's a little bit more fun. I think someone said, oh God, I'm not helping you now. Another bad one. Okay. What can you tell me about this hydrogen?
This is very positive.
It's very positive. Okay, keep going. Why is it very positive? Difference in electronegativity. Fluorine, oxygen, or nitrogen took hydrogen's electrons. What would be left? A proton. Protic. That's where it's coming from. A protic solvent is one that is hydrogen bonding capable. Okay. What about aprotic? Okay. It doesn't have hydrogen bonding. So if we put this all together, these two different classes of names, what possible solvent combinations could we get? I'm just going to call this one H, P, A, and N. What are our possible names that we could come up with? Could I have polar protic? Is that a possible name? Yes. Okay. What else could I have? Polar aprotic. What else could I have? Non-polar protic. What else could I have? Non-polar aprotic. Everybody get that? Wasn't me. Yeah? Does anybody want to be like, you're wrong?
Yes.
I'm wrong. Okay, what was I'm wrong about? Non-polar, by definition, cannot be protic. If it's protic, it has hydrogen bonding. If it has hydrogen bonding, it has polar covalent bonds. It can't be non-polar covalent or non-polar as a solvent. So we get three solvent classifications. Polar protic, polar aprotic, non-polar aprotic. Can I simplify that even further? Yes, what am I going to simplify it to? There's one. Non-polar. Yes. Polar? Which one of those three is polar, right? You're saying this one's just polar?
Well, polar protic.
Polar protic. Why could you just go protic?
Because non-polar can't be protic or aprotic. It's only able to be used in the polar.
Protic can only be used in polar, which means I can go protic versus polar aprotic versus non-polar. There's three solvent classifications. Okay. What types of bonds do I expect for non-polar solvents? Non-polar covalent. What kind of bonds do I expect for polar aprotic? Bonds. Polar covalent. Protic. polar covalent. How do I differentiate the top two? Hydrogen bonding versus dipole-dipole versus London dispersion forces. All of those terms and classifications come off of understanding what those forces are and how they stack. Kind of, sort of? You ready to just throw it all into one giant pot and mess everything up? Cool, I like it. Let's give it a shot. Not quite yet. Test it. See what you can come up with. When are we? There are 3 solvent definitions. Protic, polar aprotic, and nonpolar. Right? You have to be able to put all of those 3 pieces together. And now what happens? We get structures and you have to be able to classify. To do that classification, some jump off the page. For instance, the group I was talking to got these 2 right away. Both of those were protic. And admittedly, will be a bit nice, it was that. Protic. And I was like, okay, what do you got for the rest? And there was a pause. Okay, why did you say protic? Well, it has OH. I said, okay, next one, now.
The last one is non-polar?
Nope. We know this one must be protic. Process through what we've got. We know because there's OH, it's protic, which means if I got an OH, it's protic. That one's also defined as an answer. Now there could be a longer pause. Now I don't know what to do because now I can't use that rule of thumb where I just had protic because I have hydrogen bonded to oxygen, nitrogen, and fluorine. Now we could try and step back to the other end. Okay? And to that other end, you could say the last one was what? Nonpolar. Why?
Because it's a non-polar covalent.
Because each of the bonds in that compound are nonpolar covalent. What were those bonds in that compound? There we go. Carbon to carbon, carbon to hydrogen. Both of those are defined as nonpolar covalent. Those of you wondering about speed, that's the speed. This has to happen fast because what you're going to try and do is now apply that knowledge further on down. Okay? If it takes you too long to answer the initial classification, you can't get to the more advanced question. Kind of, sort of? You don't have to be that fast yet. 2 weeks. What's in 2 weeks? Exam 1. Okay? This is why we practice. The first one would be like, well,
Polar or
since you didn't define it, let's say it must be 2, right?
yes.
Okay? Polar aprotic. Why is it polar aprotic? The oxygens present immediately necessitates some kind of polarity behind this. Okay? Because we have a polar covalent bond. Do we have hydrogen bonding? Obviously in that. Nope, which means just the polar aprotic. I haven't specified that extra hydrogen.
Who do you want to make a call to?
Mike McFadlin. If my phone started ringing, I'd be really
Contacts
scared.
for my McDonald were found. No contacts for my McDonald were found.
You can turn it off. I was just kind of kidding. It's okay. Let's take a look at that first one now. Is it now protic? No, why not? It has a hydrogen. The hydrogen must be bonded to oxygen, nitrogen, fluorine. So not hydrogen bonding. It's still polar aprotic. Okay? Now let's make it worse. Okay. I didn't bring any slips of paper, so ignore that for a second. Go ahead and ask your question. The rest of you can look at this.
Okay, so protic, should we say that protic is hydrogen bonding capable and then aprotic is everything else?
Not everything else, because there's nonpolar also in there. You can't just say it's everything else. It's everything else that is polar covalent.
Okay. Okay. Cool.
Okay. Just the solids, ranking them. Okay, we should go through, and the very first step is looking at what?
The force.
The forces. If you aren't ready to evaluate forces right out of the gate, what should you evaluate? Bonds. Okay, so we could go all the way back to bonds. What bonds do we see in 1? Non-polar covalent. What bonds do we see in 2? Bonds. Polar covalent. You also see non-polar covalent. Why would we tend to ignore the non-polar covalent? The polar covalent is going to generate a stronger force. Next one. Polar covalent. Last one. Ionic. That one becomes tricky, admittedly challenging because I kind of botched it and should have put the counter ion on there, but it is charged, positive charge. Okay, so there's ionic. Non-polar ionic generates what kind of force? Electrostatic, which happens to be the strongest. Polar covalent generates dipole-dipole. Polar covalent generates dipole-dipole. We'll get to it in a second. Non-polar covalent generates London dispersion forces. So if I were to go through and rank that, I could go through and right away I could say 4 and 1. Or, just to be a jerk, I could say 1 and 4. What do you mean what?
Can you repeat that?
I could say, starting to write down answers, right? I could say 1 and 4, or I could say 4 and 1. Both of those are equally valid, right? No, really? That one doesn't have a higher melting point than that one?
I'm confused. Are you referring to the two middle ones where you're drawing?
Just, nope, 4 and 1. The number's 4 and 1, because we established 4 and 1. 4 should have the highest melting point. 1 should have the lowest. If I write out a sequence of numbers, 4 should be the highest, followed by 1. I could also write 1 and 4. For those people maybe now starting to recognize this, if we go through and write out an answer for this, let's actually push this to the rest of the way. We'll clear out the bottom for a second. 4, 1, 1, 4. How do we deal with 2 and 3? 2 has the added bonus of hydrogen bonding. Hydrogen bonding is stronger, which means 4, 2, 3, or both of those answers are equally valid. That highest to lowest, depending on how you read questions and answer language, becomes very challenging. Okay? Which is why if you're given an open-ended question like this, you should really make sure you clarify it to make sure we've got the ranking. I try very hard to include brackets so that we can ensure that we're all in the same language. Okay? I want you to be aware of that language issue. Make sense? Okay? Both of those are acceptable ways to represent it. We've got the sequence going in opposite directions. Okay? And yes, I feel it's obvious. Trust me, I've graded. It's not obvious. Okay? Does that make sense? You would repeat that for the liquids. Let's make it more difficult, because now you should be able to do that. Let's take a look at the solubility for 3. I now want these things to mix. I deleted all my forces. That was awesome. All right, we had, what was it? Electrostatic, dipole-dipole, hydrogen bonding, and London dispersion. Like forces dissolve like forces, right? What forces do I see in A? Dipole-dipole. B. Hydrogen bonding. C. D. Okay, so I could say 1D. That's a nice straightforward one, right? What else could I do? Two, B, or C. Why'd you give me 2 options? They're both hydrogen bonding. Okay? It doesn't have to be a perfect alignment. Okay? B or C could potentially work. Okay? What else could I do? Okay? We could say 3 to A. Right? What else do we have? I heard a 1 to B. Is that what I heard? 1 to B? D. Did I already do that? I did that one. okay. It's right there. Thanks for catching that fast. How about the last one? 4. Had electrostatic. What's the closest force to electrostatic? Hydrogen bonding. We have 2 hydrogen bonding. Are they the same hydrogen bonding? No. C actually has more opportunities for hydrogen bonding, more polar, which means 4C probably makes the most sense. Okay? How would we know
How do you know what?
that these answers are valid? What's that? We would test it. Solubility becomes one of those very questionable things. You just got to test it in the lab. So it makes it more difficult on an exam. So you'd get real black and white comparisons, not gray areas. Make sense? Cool. I'm just going to say that was a yes. Okay? Applications. If we take a look, these 2 reactions are going through different systems. Okay, if we actually match this up. They end up doing the exact same thing, but they have a different process by which it happens. Okay? In one case, it happened in 2 steps. In the other case, it happened in 1 step. How do we know that? How do you know you have a step? You're like, it couldn't be that easy. How do you know you have a reaction? You have an arrow. How many arrows do you have? 1 or 2. One is 2 steps, one is 1 step. How do we know it was 1 step or 2 steps? 152. You remember all that kinetic stuff that you did? 152 with our rate laws, that's exactly how we would figure it out. Don't panic after spring break. And we'll skip 152. Okay, we'll just say that they exist. Okay? These have different results. We see different things happen in each of these cases. In the 2-step one, I see a positive charge. For that reaction to work, the positive charge must exist. Okay? So it would be nice if I had something that could help stabilize that positive charge. What would need to be in solution to stabilize that positive charge? A negative. Would a nonpolar solvent work well? A nonpolar solvent has no charge, which means it can't stabilize that. A nonpolar solvent does not facilitate the second reaction. We use our solvents, and the solvents will dictate which reaction works. That's crazy. That's why we need to know our solvents. Okay? And those solvent classifications. Are they always straightforward as far as solvents and dissolving in water? No. A lot of times they're all over the map, and it can become very challenging. Okay? For instance, ethanol. We're just going to do shorthand and fast through here. Ethanol does dissolve in water. Chloroform, nice polar bond there, but they all cancel out. Non-polar, or ends up being not dissolvable. Acetone. A lot of non-polar parts, a little bit of polar parts, dissolves in water. What the hell? Diethyl ether. Four carbons, 1 oxygen, doesn't mix well with water. But if I take 4 carbons and 1 oxygen and I just change the orientation, throw in another bond, purple one does mix with water. Same number of carbons, same number of oxygens, just 2 less hydrogens, and now all of a sudden it mixes with water. Solubility is not a perfect, these are the forces, so they must mix. There's all sorts of other stuff that goes into it. What's that other stuff? Lab. This is why our first lab is looking at solubility and looking at some of those nuances. It is not black and white. It is not particularly easy. We come up with the best approximations we can, and we work from there. Right? What can be done with the interactions? This would be the fun application slide that I just kind of want to whip through. Okay. If we look at micelles, That's how soap works. Soap has a polar head and hydrophobic tail. That hydrophobic tail dissolves the dirt, oil, and grease, and the hydrophilic head makes it water soluble, so it washes off your skin. If we make the micelle big enough, we can get 2 layers, and we can get liposomes. What the hell's a liposome? Good. Biology hasn't ruined you yet. Right? If you continue to make that bigger, you can get bilayer sheets. And what the hell's a bilayer sheet? It's just a fancy cake. Good. You don't know it, biology hasn't ruined you yet. Okay? Those are all based off of intermolecular forces and the hardcore application of how these things stack and interact. Absolutely fascinating and cool. Unfortunately, we don't have a lot of time, which is why I really want to dig into the part that everybody's going to hate, where our electrons exist. Electrons exist in orbitals. Right? So we've got atomic orbitals. Yay, atomic orbitals. Right? The problem with atomic orbitals is that atomic orbitals don't do a good job of representing the shapes of molecules. The bond angles, or the angles between any 2 p orbitals, is 90 degrees. The bond angles in a methane, 109.5. So our atomic theory does not mesh well with our molecular understanding. Okay? But for a molecule to exist, the electrons have to exist in orbitals. So there has to be some way to make our atomic understanding match molecular understanding. There's 2 approaches to that. There's the linear combination of atomic orbitals, molecular orbital theory, which involves supercomputers. It's neat, it's fancy, it's fun. Nobody likes it, so we don't use it. We don't, like us, won't use it that much. Okay? The other way is to say, well, I know it has to work, so what am I going to do? I'm going to make it work. Making it work, hybridization theory. Okay? So if we looked at methane, we've got carbon in the middle, 4 bonds, all equally spaced. Right? Carbon, 4 bonds. Yeah? Does it look like some people wanted me to draw that? There it is. Those all have to be 109 degrees away from each other. There is no way I can get these orbitals to be 109 degrees away from each other. Okay? It's not going to happen. So something has to happen to force that to exist, because I know that exists and I know that shape. Okay? That something is a combination of atomic orbitals. Okay? Specifically how? We're going to take the valence orbitals. Why the valence? Those are the outermost. Those are the ones most likely to interact. Do the other ones also interact? Yes, they can. They absolutely do. I don't have a supercomputer. I'm not talking about it. Okay? So what we just want to do is take those and somehow make that happen. How many atomic orbitals do I have? 4. How many new orbitals do I need? 4. There's 4 bonds. I have to explain where those electrons go, right? Okay. Orbitals are effectively matter-ish, sort of. Okay. So we can't create or destroy them. So if I start with 4, I have to end with 4. Since I need 4 at the end, I'm going to take all 4 of those, I'm going to throw them into one giant pot, and I'm just going to say I'm going to make some new stuff. Okay. In that making of new things, I'm going to make sure that when I make them, they align to the proper angles. Okay. And I'm going to create new orbitals. Okay. There are my new orbitals, all beautifully drawn so that you can tell the 3-dimensional characteristics. Thank you. 1 smile. That's good. Okay. What do I want to call those new orbitals? Are they s orbitals? Are they p orbitals? No. I could call them anything I want. Scientists decided to call them based off of the orbitals that made them. What orbitals went in to make those? 1s and 3p orbitals. So I'm going to name each and every single one of those sp3. How did I get that shape? We're going to end with the shape on this in just a second here. Let's just take a look at one of those. We have an s orbital. Okay. Orbitals have this fun thing called phases. So I'm going to say it's positive. We're in OCHEM. We've got to be optimistic. Okay? And then I have the p orbital. What's special about the p orbital? It has a node going through it. That node means the phase changes. So one side of it is positive, the other side is negative. Okay? What are we talking about when we talk about phases? This is positive, this is negative. What happens if a positive overlaps with another positive?
It's bigger.
It gets bigger. So when I talk about bringing these two together, this area here is a lot of positive overlap, which means it gets bigger. Trust me, that's bigger. What happens down here? That's positive overlapping with negative, so it gets Thank you. With that, we have to stop.